Math Analyzers, and welcome to your Chapter 7, Lesson 7 notes. We are going to solve our logarithmic equations. Everything we've been doing about logs, so lessons 3 through 7, I know, I'm even going back to my exponential equations lesson, has led us to being able to solve logarithmic equations. Now we're going to have 2 lessons on this. One all about solving logarithmic equations, and another one where we'll look at solving our exponential equations again, but this time the situations where we have to use logs in order to solve them. Okay, so we'll take another look back at those. Let's start with our usual reminders, right? Logs into exponents. So the base of the exponent is the base of the log. The exponent itself is the answer to a log, and the answer to a power is the number inside the log here. If there is no base written, we assume it's base 10. That's the common log. If it's ln, that would be a base of e on the log, that Euler's number. And again, e is a constant, just like pi is. It's just an irrational constant. Okay? It's called e, Euler's number. If I haven't yet, I will assign you guys the Euler's number video. Good explanation as to what that is. Oh, another reminder. Raising a base to a log with the same base cancels out. That's another thing. That's another quick reminder. So in exercise 1, we'll kind of think back to when we looked at these, and we looked at these a couple of times. But if you have a base raised to an exponent that has a log with the same base, then these two things actually cancel each other out, and whatever the answer is in the log is actually the answer to evaluating or simplifying this particular problem. Now, if it's not the same, like here, you make this base the same as the log base. So in this case, 9 is not the same as the log base 3. Yeah, well. So now what can we do to 9 to have it have a base of 3 as well so that they can match and cancel? Well, 9 is actually 3 squared, right? So we replace 9 with 3 squared, but we've still got this exponent to consider. We know now from the properties of exponents that this number here is actually an exponent on this number that's inside the log, but now the 3 and the log base 3 are there to cancel each other out, and 81 squared is not something that I know off the top of my head. Sorry about it. 81 squared. 6,561. I mean, duh. There's our answer. Okay? So here, cancels out. 729 left over. Here, e to the ln. Yeah, that's log base e. Cancels out. 25 is left. Darn it. You knew you had one of them coming, right? So let's see. 2 squared is 4. So let's replace 4 with 2 squared. And then, of course, we've got this log base 2 to the 10. Now, this 2 in front and the power rule means that it is an exponent on the 10, and the base and log base 2 cancel each other out. So now you're just left with 10 squared, which is 100. Okay? And just to give you the quick reminder of why that happens, I want you to think about, let's do this one. This is a pretty good one. Log base 3 to the 729, right? So 3 to the what power gives us 729? Well, that would be, so it's 3 to the 6th. I couldn't remember which one. That's why I'm testing. There we are. So that means that log base 3 to the 729 gets replaced with a 6. That's what it's equivalent to, right? Well, 3 to the 6th power is 729. So either way, you get this, which then creates that rule for us that if the base and the log base you're raising it to are the same, that cancellation can occur. And that gets us things like this, where I actually couldn't have replaced log base 2 to the 10 with an integer. Okay? So that gets us that ability to do that cancelization and get in there with the rule rather than have to go through all the changing, get a decimal, and then end up having to go through the process with that decimal and squaring it to get 100. Okay, would have ended in the same place, is essentially what I'm saying. So we now have that shortcut and we're going to use it. We're going to use that shortcut because notice log base 11 to x. So I set this equal to x, like from exercise A, is equal to log base 11, 121, right? Well, that means the log base 11 parts can cancel out. And what's x equal to? 121, which is exactly how we did that. We've been solving exponential equations. Now we're actually going to put that variable in there. And we're going to use this idea that the base raised to the log of the same base cancels out, and that answer comes out. We're going to use that idea the same way we use the exponential equations idea. Getting that same base, now I can set my exponents equal to each other. Okay, so we're going to use that idea again, which is just a really neat process. The only thing we really need to consider as going through this is make sure the log is alone. So this is where we have to do that consolidation stuff that we learned using the product rule and the quotient rule and the power rule. We need to make sure the log's alone first, and then we can perform this activity where we put these two things on each side of the equal sign as exponents on the same base. And we pick a base where the log bases will cancel out with us. Okay, so in this example right here, both of these logs have a base of 2. So they have the same base. So I pick 2 as the base and put those things in the exponent. Now what happens is 2 raised to the log base 2 cancels out, and just this x minus 5 comes down. 2 raised to the log base 2 cancels out. Just this 2x comes down to the next line. Now get all the x's together on one side of the equal sign, and you know what x equals. X equals negative 5. Okay. It's possible to have logs on both sides of the equal sign or logs on just one side of the equal sign. Okay. If you have multiple logs on the same side of the equal sign, that's the make sure they have the same base and consolidate them. Okay. So we'll look at examples of all of this stuff and as it gets used, right? My favorite example will be, and I'll show you this when I do it, it will be stuff like number 2. And that's kind of where on your final exam I use this. Just starting to think about that. Exercise 1. These both have a log base of 10 because it's not written in. So I know this is a common log that's going on right here. So since they both have base 10 and they're both consolidated as much as possible, what I'm going to do is take 10 as an exponent base on both of them, and I just made this the exponent for 10. I made this the exponent on 10. Now the log of 10, the log base 10 and 10 there cancel out, and just a is left. And here, same thing, and just the answer is left on the other side of the equal sign, which is 4a minus 9. Now all I have to do is get a by itself with the usual linear simplification. Subtract 4a from both sides of the equal sign. I get negative 3a equals negative 9. Divide both sides by negative 3, and voila, a equals 3. Next. Take your time. Make sure you're doing this with me. I know I've got the answer over here too, because I know that this stuff is brand new and sometimes challenging. So I really want to make sure you can see what I've just done right? I've just made this my exponents with that same base purposefully to use that cancelization we just practiced on purpose. There are two ways I can solve exercise 2, and I'm going to show you both ways. Okay? The first way is to recognize, oh, okay, my base is 5. Cool. So I'm going to use 5 as my base and put these two things in my exponent. Well, on this side, that doesn't mean a log in the exponent. That means a 2 is now the exponent on this base of 5. So over here, the cancelization happens and x plus 1 is left. But over here, you've still got 5 squared. There was nothing to cancel. There was no log base 5 that could cancel with. So this is it. 5 squared is 25. X plus 1 equals 25. We'll subtract 1 from both sides and x equals 24. Now I know that's the way I did it over here, but there is another way you can handle this. And that other way you can handle this is to remember that a log is an exponent and an exponent is a log, right? So I'm just giving you my classic example of that. Switch it back into an exponent. Only one side has the log base 5. So you know 5 to the answer 2 is equal to the number in the log, x plus 1. I just converted it back into exponential form. That's all. And 5 squared is 25. And oh, this is exactly the same problem that I had before. Because that's the relationship between treating these as exponents or treating these as logs. That's why we have the log as a possibility to treat these exponents. So we have that, because we have that ability, this actually could just turn back into exponential form and I can solve. And that's another way to get my x alone out of the log. Okay? More, of course. More examples. Do the examples with me, even though I know they're right next to it. Here's where it starts to get more complicated, right? And it does. It's obviously it's algebra 2. It's going to get more complicated. But this is just your power rule, right? This 3 out front, okay, well, that's okay. I just know I've got 3 of these log things that are then equal to the 6, right? We'll just start out dividing both sides by 3 to get the log alone. Isolate the log first. So let's divide by 3. Now you got log base 10 to x plus 4. You know, I just say base 10. We obviously don't usually, even though it's not written, right? Because it's the common log. Then you've got 6 divided by 3 is 2. Okay, so now this goes back to the same thing that we had going on in the last problem, which is we know we've got base 10. You have 2 ways you can treat this. Either raise both of these up on a base of 10 exponent wise, that cancels, leaves you with x plus 4 equals 10 squared is 100. Subtract 4 from both sides, you get x equals 96. Or right at this step right here, I'm just going to rewrite it in the red so you can see my other way I can treat this. Change this whole thing back into an exponential form. So 10 is my base of my log, 2 is the exponent on the base, and the answer here is x plus 4. And notice it's exactly the same problem that I had over there, right? X equals 96 either way. So 2 options as to how to view it. 2 options as to how to view it. And again, that's when you have log on one side only. Okay, when you have log on one side only, that's an option for you to use. Okay, it's not an option for you to use when you don't have that. As complicated as it will get with us would be here. I see a plus sign between 2 logs. So a log is not alone. There's multiple things going on. That means I need to use the product rule to condense those. Thankfully, they have the same base, so I can easily do that, right? So they both have a log base of 3, and we're adding. So that means we write it as log base 3 to x plus 8 times, the answer there is x. And all this equals 2. Well, now my base is 3, right? So 2 ways I can handle this. One way would be put both as 3 and put those things up in the exponent. This cancels, and oh, I'll distribute as I go. X times X. Well, here, you know what? No, let's not jump the gun. Over here, I do need to deal with 3 squared, which is 9. But now, look, this is just a quadratic equation. So distribute the x squared plus 8x, and we know we need to subtract this 9 over, equals 0. It's a quadratic equation. It's factorable. The factors of 9 that subtract to give me 8 are 9 and 1, positive 9, and negative 1. And so in doing this, I get 2 answers for x. X equals, oh, sorry, I tried to skip a step, and I'm not supposed to do that, so I won't. I can't do that with the zero product law. You know, you got to prove it, man. I get 2 answers for x. Only one of them can I keep. And the reason I can't keep the negative 9 is because if I plug the negative 9 back in here, I can't have a negative answer part in my log. So if one of my answers yields a negative answer part in my log, and it would do it in both spots, I'd get a negative 1 here, I'd get a negative 9 there, that can't be kept. That gets rejected. Okay, that's this stuff over here. Things to remember about the logs that we talked about, or down there, excuse me. That's the stuff that we talked about in that very first lesson, introducing us to logs, that base had to be greater than 1, not greater than or equal to 1. And that your answer in the log has to be greater than 1. Excuse me, greater than 0. Okay, so that has to be positive. All right, this part right here. So we know that we are going to have to be on the lookout for those extraneous roots and possibly reject as we go. Pay attention to that last one. Look at what I did again. Look at what's going on over here, because again, same deal like that, right? Okay, raising that power to a log of the same base. Make sure you try these. Make sure you write them with the notes. Then make sure you try these. You've got 2 homeworks to test this on, okay? Ask me for help. I am so happy to help you go through these, all right? Logs are tough that first introduction. We'll get there. And again, here's a spot where I need to consolidate, condense, make smaller my logs using my properties. All right, that's why we needed to learn those first. All right, there it is, lesson 7. Very heavy on this whole part right here. So make sure you remember that whole part that we talked about back in lesson 5. All right, I think you can do this, but if you can't, I'm here for you. All right, guys, I'll be seeing you. Bye.